Here's our 361 design project. We call it Zeus's Highway.
Cool. So basically the problem we were looking at is related to electric vehicles. And so the major problem within the electrical vehicle market is that electrical vehicles are limited in their potential range and cannot conveniently do long distance travel. Road electrification provides power to electric vehicles as they travel on the road. And so the challenge we're really focusing on in this problem space is how energy could be transferred from an electrified road to an electric vehicle, assuming they can process the power. And our eventual long-term goal would be to power an electric vehicle while moving on a highway. And so we looked at different ideas and looked at different ways we could go about this. And what we were really inspired by was looking at Volvo Group electric road systems. And so what they do is they use contact charging. And so in essence, there's two power rails on the road that basically power the vehicle.
So after looking at that Volvo design, we were inspired to create our own, and we went through our first prototyping stage. So what we did is we tried to simulate an electric vehicle by using an RC car, and we wrapped the tires of the car with wire and then powered 2 aluminum strips on our road. And then with using the power strips, we were able to run the RC car without needing any power within the vehicle to simulate our idea.
Yeah, and so we went through this process of creating our first prototype, and we conducted user interviews. And so the major key points that we got out of that was that there were several issues that we needed to address, but 2 of them that we really focused on were traction and pedestrian safety, because of the modifications we made on the tires, there was many issues or many concerns that traction would be affected. And second of all, people were scared that electrifying roads could cause a lot of safety hazards and people could get hurt. And so in our next iteration, that's what we decided to improve upon. And
cut. So we moved on to our second prototype iteration, and what we did to address the traction, safety, and reliability issues is we added different conducting material to the tires to simulate the actual conductive rubber that we wanted to use. We widened the rails of our tracks to increase the room for error of our driver, and we added a transponder just for an extra safety feature. So as a user enters our lane, it drives along the track and will receive a beeping notification from our transponder that it is using our power rails, and we receive their information associated with their transponder to charge them the effective rate of the electricity they're using. So to simulate this, I have a remote control. We have our 3 AA batteries powering our rails. We have an RC car with no power in it, as shown with no batteries in it, and then we can just use the remote control to drive it. So as we get to the transponder, it beeps and it'll keep driving. So here we have our just proof of concept picture of our system, shown with the rails and the electric car on the road along with their charge rate. So how this actually works in the coupling system, there's shown with this GIF, there's electrical brushing that transfers the conduction from the tires to essentially the drive shaft of the vehicle to the induction motor. So the electrified rails run along the length of the lane, and then the 2 conductive wheels make contact and complete the circuit with the road, and then the power travels through the wheels and the brushing into the motor. So to compare our first 2, our prototype 1 and prototype 2, the main changes that were made was an original prototype. We used 22 American wire gauge, and we increased the diameter of the wire and went to 19 American wire gauge, just to allow for more heat dissipation. Originally, we didn't know the track material that we were going to use, and we decided to use high-strength steel. We also didn't know the length of the track, and through calculations, we came up with 300 meters sectioned off each a meter apart from each other. We developed a new communication system with a working transponder. We also incorporated a speedometer with this transponder to enhance safety, and we were able to calculate necessary voltage and current needed for maximum power consumption of the vehicles.
Cool. So we also looked at looking at safety and how we can improve the safety of our project. And so the way we'd address this is really looking at our rails, and what we basically did is we sectioned our rails into strips just in case anything does go wrong. It'll be easier to short circuit
To break the circuit so that there would be no current flowing through it anymore.
Exactly. And so looking at our transponder as well, so our transponder actually has three parts. So the first part is the speedometer, which actually checks for the speed in the car. There's a frequency transmitter that communicates with our actual network, and there's actually a switch to turn on the rails when car is on it. And so we also looked at connectivity and traction, and trying to improve our prototype and making sure that our tires are actually have traction. And so for our rails, we found a special type of steel that we would be using. It has very good traction, and our tires themselves would actually, in the middle diameter or circular region,
In the middle width,
there would be conductive rubber that would actually be able to complete the circuit. And so for costs of the car itself, we estimated that it would be around $1,900 per car, including all the tires, the brushing, the installation, the transponder, and everything. And in terms of the actual road, it would be about $12 million per kilometer.
$12 billion.
Continuing on for testing and results. So the engineering challenges and shortcomings that we figured out, and I guess problems with our ideas, is that our feasibility is really heavily reliant on external factors, such as government compliance. We're making big assumptions that the government will actually want to implement these roads, and there's also the big assumption that car manufacturers will eventually and hopefully modify their cars so that they can actually accept electricity. Second of all, the implementation of the full-scale model is very high risk, and so there needs to be a lot more analysis done to make sure that this makes more sense for the government and for consumers. Furthermore, scalability of track effectiveness is difficult to prove, and our accuracy of cost predictions that we've made are diminished by the fact that there's insufficient real-world examples, and there's a variety of possible materials to use for our solution. We've done very selective research, and we found solutions that we think will work for sure, but we would need to do further testing to make sure that it's the proper material. And finally, in terms of our prototype, it's difficult to implement an actual transponder and it's the actual functionality. So for our next steps, what we want to do with our project is we want to actually implement the chosen materials into our prototype, construct a medium fidelity prototype, something that reflects more of the real world even more. Maybe focus on issues related to the weather conditions, and ideally perform long-term testing on a prototype to actually get results and see how effective our system would be.
We want to be able to upscale it to use actual car tires and actual vehicles so that we can show a real-life example instead of just a small model.
And that's it for our demo.
Thank you.
Thanks.